Okay, so the goal for today is just to continue on with differential equations, hopefully get through, kind of finish up our little introduction and then move on to separable equations and get through that. So that's kind of the goal for today. The supplement on first order linears, as well as a couple of applications of separable equations, is available on the YouTube um, playlist, the supplements playlist. So you can take a look at that for how first order linear equations work. And then the goal for our first class next week, and probably a supplement next week as well, will be second order differential equations. Uh, so that's going to be kind of the scope of our discussion on DiffEq in general. The quote of the day today, the kind of idea of the day is from a past colleague of my wife's. She would say, velocity is a vector quantity. And what she meant by that is velocity consists of both speed and direction. So there was kind of a joke saying that, a lot of times in kind of big institutions, people like they kind of look down at their feet and make sure their feet are moving really fast and they feel like they're achieving something, but it's like, well, are we just doing this to do something without, really having the goal in mind? So, have we actually pointed ourselves in the right direction, or are we just, doing this work to make ourselves feel like we're accomplishing something and actually we're going in the wrong direction and putting in a lot of effort to get nothing done? And I think this is related to uh, kind of these couple of thoughts of mine, that effectiveness, or your ability to achieve a goal, is something like the product of efficiency and effort. If you spend all of your time and effort pointing yourself in the right direction or hyper optimizing your strategy, but you never take a step forward, you don't actually get anywhere. So if your effort is zero, it doesn't matter how efficient you are, or if your speed is zero, it doesn't matter what direction you pointed yourself in, you're never going to get where you want to go. And on the other extreme, if your efficiency is zero, if you're just, running as fast as you can, we have no idea where you're going, you're probably not going to get very close to a goal if you're pointed in the wrong direction. So the optimum is to have some kind of balance of the two, right? And if you tend to be the kind of person who just jumps into things head first and doesn't really plan first, maybe recognize when you're doing that and take a step back and say, all right, I'm going to take 15 minutes, a half an hour, and strategize a little bit before jumping in. Or like is my tendency, if you're the kind of person who likes to spend a lot of time thinking about the plan and struggles to take the step forward until the plan is perfect, maybe say, okay, the direction we're pointed close enough in the right direction, we can start walking in that direction and course correct if we need to along the way. So this works for, if you want to learn to play the piano, or if you want to learn coding or something for your career, or whatever it may be. But I think particularly when we're thinking of career related things, there's also something else to be aware of, and that's impact, right? If you are an engineer and you go to your boss and your boss says, for your performance review, and your boss says, what have you done this past year? And you say, hey, I'm great at playing the piano. Now I put in a lot of effort and strategy into learning how to play the piano. And your boss is going to say, well, that doesn't help me. That has low relevance, right? So if you want to increase your impact to your employer, or to further your career, to increase your salary, something like that, um, again, balancing effectiveness, which itself is a balance of efficiency and effort, with relevance. What are the things your employer cares about? Of course, that's not to say that the only things you should do in life are those relevant to your career, not at all. But if your, goal for doing a certain thing is to further your career, you know, ask what are the things that your employer really cares about? What are things they find relevant? And how can you, uh, you know, boost your efficacy in those areas? Okay, so on to DiffEq. So just to quickly recap, what is a differential equation? It's an equation relating a function to one or more of its derivatives. And importantly, as we saw last time, the solutions to such an equation are families of functions. So for instance, the solution to y prime equals y is the family of functions y equals a times e to the x. Why is that a solution? Because if I substitute this into the differential equation up here, the two sides represent the same thing. I get a e to the x on the left, and on the right, So it's a solution. Note the single degree of freedom here. The family of functions is parameterized by one constant a, because we, in some sense, had to undo one derivative. That's a single constant of integration. And kind of analogously, we had a second order equation, y double prime equals negative y, for example. We saw there were, in some sense, maybe a couple families of solutions, but then we realized, wait, actually, I could combine these together, and really this is just a family of functions, a times sine of x plus b times cosine of x, that has two parameters, a and b. There are 2 degrees of freedom here. These 2 arbitrary constants come from undoing 2 derivatives, so basically 2 integrals, 2 constants of integration. And we mentioned that a sine x plus b cos x using just trig can be rewritten as alpha sine of x minus phi. So just a single trig function with an amplitude and a phase shift. And it's actually a simple harmonic oscillator. So very important kind of canonical differential equation and important canonical family of functions in very many applications. So that's a quick recap of what we did last time. And we spent quite a bit longer than that last time on this, so that's just a recap. So what are some applications of differential equations? Not going to go through these in really any depth, but just to mention some, you might find ones you find interesting and you can Google them or look in a physics textbook for more information. But Newton's laws result in are often modeled by differential equations. I kind of listed them under ODEs because we can think of them in, say, one dimension, but certainly could be applied to PDEs as well, partial differential equations with more than one independent variable. Mass spring or pendulum models, mixing problems, things even like pharmacokinetics, the way that your body handles medication when you take it in, or the way your body eliminates that medication. This is kind of a mixing problem type problem. But the kind of the simplified mixing problem is we just have a big barrel that has maybe some input, some output, and some, amount of stuff in it, say like a saltwater solution or something like that. So we have water coming in, or maybe salt water coming in. We have the mixture leaving the tank, and we have maybe some salt already in the tank that's kind of being mixed around. So what does the concentration of salt in the tank look like over time? That might be a mixing problem. RLC circuits, just kind of your standard electrical circuits with resistors, inductors, and capacitors in them. So these are some models from ordinary differential equations that we'll see come up. There are some PDE models as well. The kind of more famous equations tend to be PDEs because, well, we live in like 3 spatial dimensions plus time. So we have usually more than one input. Even if we're restricting ourselves to one dimension, typically we have a spatial dimension and then also a time dimension as inputs. So even in kind of a one spatial dimensional model, we often still have a partial differential equation because we have more than one independent variable, say space and time. But things like Maxwell's equations, the equations modeling the uh, uh, electromagnetic force. I don't know why I wanted to say like electromechanical, not the right word. The Navier-Stokes equations, the equations modeling fluid flow, fluid dynamics, Schrodinger's equation, fundamental to the study of quantum mechanics, the heat equation modeling the propagation of heat in a medium, or the wave equation. Schrodinger's equation is kind of a form of wave equation, but there's the kind of wave equation that describes like if you pluck a string on a violin or if you beat the membrane of a drum, how that might how those forces might propagate, how those membranes or those strings might oscillate over time. So these would be partial differential equations because we have at least one spatial component. Like a string, we might model it as one dimension, or a drum head as 2 dimensions. Super interesting uh, whatever. I just lost the word. But anyway, so there are very interesting differences in the dynamics of 1D versus 2D that actually come into how these instruments are played. Like if you're playing a timpani, you don't hit it right in the middle because it won't really make much of a sound. That's kind of a dead space because of the way that these wave equations work. But if you're plucking a string, you could pluck it in the middle, and that's perfectly fine to do. Um, but anyway, um, and some others, things like epidemiologic models. So things like the SIR model, modeling populations of susceptible folks, infected folks, and recovered folks who might have developed immunity and are no longer susceptible, or the SIS model if you don't develop immunity uh, when you get a disease. In finance, the Black-Scholes model, which is actually a stochastic differential equation, a completely different kind of equation. What you would do is reduce this to a PDE and then solve the PDE. Um, so tons of applications of differential equations. And there's a phrase that I'm paraphrasing here. I read this somewhere, and for the life of me, I cannot figure out where I read this. Probably because I don't remember it close enough for Google to recognize it. I thought it was from Feynman, Richard Feynman, the physicist, but I can't actually find this quote anywhere. I thought it was from one of his lectures. He gave a series of lectures on the nature of physical laws. And I thought it was from one of those, but haven't been able to find it. But so maybe a paraphrase of something from Feynman. Um, and that's the idea that science is phrased in the language of mathematics, and in particular in differential equations. So really this idea of differential equations is, I would say, ubiquitous across science. You might not see the differential equations nature in maybe an algebraic treatment of, say, physics or chemistry or something like that that doesn't presuppose calculus and differential equations. But if you dig deeper, if you say, wait, they told us to use this equation and maybe gave a heuristic argument for why it should be true, but why is it actually true? A lot of times you start digging and you see, oh, there's a differential equations model under there, and this is the solution to it. Okay, so a little more information on kind of background. I'm going to leave most of these as exercises because I want to get through this relatively quickly. But the general form of an nth order ordinary differential equation is that some function of the derivatives from the first derivative through the nth derivative, the dependent variable itself, and perhaps the independent variable equals 0. Or we could solve for the nth derivative as a function of everything else. But the things that appear could be the independent variable, the dependent variable, and derivative or derivatives of the dependent variable. Up here, we actually saw that the differential equations we looked at as our kind of initial examples that we just guessed solutions to only explicitly involve the dependent variable and its derivative or second derivative, no explicit dependence on the independent variable. But we could have explicit dependence on the independent variable as well. Something like that would be a perfectly fine differential equation to exist. It would make it considerably harder to solve, but it could, it's a fine differential equation. And we talked a little bit about functions before, functions as solutions before. When we can write a function like y equals, say, phi of x, we call that an explicit solution. And I'm going to leave these as exercises. So you can show that this potential solution does actually satisfy this differential equation. And you might recognize this. This is just saying that the acceleration is g, constant, like gravitational acceleration. Under gravitational acceleration, the position looks like a quadratic in time. Something closely related to to one of our examples above that we had guessed a solution to last time, we guessed a solution to y prime equals y, and that was y equals a times e to the x, or a e to the t, whatever we want to use for our independent variable. What if I have a constant that comes into play here? What if I have a parameter that comes into play, like the letter k here? Here I have p of t, so p is my dependent variable, t is my independent variable, and k is just a constant, it's a parameter. Guess a solution to it. It's probably going to look like an exponential because we have the first derivative looking more or less like the original function, but it's not going to be k times e to the t because we know that p prime equals p, where k would just be 1. That has solution like constant e to the t. Where should this k go to make this work? So give that a thought, write that down in your notes and come back to it, do it as an exercise. We could also show that something like this, y equals c1, constant 1 times sine of 2x plus constant 2 sine of cosine of 2x, solves, for instance, y double prime plus 4y equals 0. This actually might give you a hint that you can use to guess example 2. Okay. And then I ask a question here, what if we change this plus to a minus? Would we get more or less the same solution, or would we get very different solutions? It's an interesting question. That seems like a pretty minor change, just changing a plus to a minus. Is that going to drastically change the nature of our solutions, or will we get more or less the same solution, or even exactly the same solutions? Good questions to ask. And these are all questions that we can address without having developed any of the material about separable equations or any of that. This is just getting a gut feeling for differential equations. And then this question, is this a solution, or can we even find a solution to this differential equation? And a little hint, and by the way, we're talking about solutions over the real numbers. A little hint, don't think of differential equations here or even calculus, think of just algebra. So can I make the left side and the right side be the same thing, just algebraically? We can always apply algebra ideas to our differential equations, of course, because they are, by their nature, equations. We also could have implicit solutions where we have some relation between, say, the dependent and independent variable that's not an explicit one. So for example, a solution to y prime equals negative x over y is actually this circle, x squared plus y squared equals c. This circle is not a function properly speaking, right? It fails the vertical line test. I could chop it into two explicit functions, a top half and a bottom half. Each of those would be explicit solutions by themselves, but this full circle is an implicit solution. Okay, and here's where we're going to start kind of picking things up and working carefully through these problems. So the last several questions were really for you to kind of chew on and think about a little bit and get a bit of a gut feeling for how these things work. And now we're going to look at initial value problems. So what is an initial value problem? Well, let's scroll all the way back up here. And remember, we had, for instance, a first order differential equation that had a solution that looked like this, really a family of functions as of solutions. Or a second order equation that had solutions that looked like, let's just use this version of it. that had a family of functions that represented solutions. I could choose A or A and B any way I like as real numbers, and I would get solutions to the first or the second differential equation. Now, this is actually kind of nice because maybe this equation here I want to use to model a mass spring system. That was one of the models that I mentioned last time. This might be a model of a mass on a spring kind of bouncing back and forth. Well, I could imagine that maybe even if I take the same mass and the same spring and, you know, that system is well modeled by this equation, that same mass and spring, I could just set the mass at the natural length of the spring and let it go, and it's not going to do anything. Y equals 0 would be a solution there. Or if I stretch the spring a little bit and let the mass go from rest, it's going to start oscillating a certain way. If I stretch it more, it's going to have bigger oscillations. If I start the mass at the equilibrium at position 0, but I push it so that it immediately starts, say, compressing the spring, then it's going to bounce back and forth. If I push it a little harder, it's going to bounce back and forth more. I can imagine there are a lot of, even with this particular spring and this particular mass, there are a lot of scenarios that I could come up with as in experiments or in the real world that I kind of would expect this model to be able to handle. Those scenarios correspond to different choices for A and B. If I push it a little bit harder, maybe A and B have to be a little larger in magnitude. Or if I, start at equilibrium and push it versus if I stretch it and let it go from rest, maybe that says something about what A has to be or B has to be. And in fact, the way that I find A and B is I look at those initial conditions. How far did I stretch it at time 0 and how hard did I push it at time 0? Those two constraints are where I use these degrees of freedom, A and B, to match the model, this solution to the differential equation, to the constraints, to the real world experiment. Or likewise, if I was using my first order equation up here to say model population growth, well, maybe I would want to know what is the population at time 0 so that I know which one of these solution curves it's at least that our model is going to suggest that it will follow. So I use initial conditions, maybe initial position or initial position and speed, to determine what member of that family of functions I want to pluck out and use as my model for that specific scenario. So the kind of general solution to a differential equation is a family of functions. And if I want to impose some initial conditions, then I have an initial value problem. I have an initial condition coupled with a differential equation. All right. So let's look at this one. If I want to solve this, how do I go about that? Well, the first thing I want to do is solve the differential equation. I want to figure out what is the family of functions that are solutions to this differential equation. And then I want to pluck out the particular member of that family of functions that satisfies this constraint. So here we'll use the independent variable t and the dependent variable x. So I see that x's derivative is -2 times itself. dx dt equals -2x. This feels like it should be an exponential function. But if I do something like a to the t, it doesn't quite work because x prime is just x. Maybe I say, okay, maybe I'll do -2 a to the t. I think that would be a logical first guess, but I actually see for a couple reasons this isn't going to work. One, it just fails pragmatically. X prime is still just x. We can just observe that. Or a little more abstractly, well, a is just an arbitrary constant, so -2 times a is just some other arbitrary constant. This is still really just some arbitrary constant times e to the t. So I need to put this -2 somewhere. It's got to pop up somewhere in the solution. And hey, if I do that, when I take the derivative, the chain rule pops out a factor of -2. And that looks right. So I'm pretty confident that this is my family of solutions. Again, at this point, I haven't done any, I don't have any kind of rigorous or algorithmic way of coming up with a solution. I'm just using my knowledge of functions and how their derivatives relate to them uh, to do basically using intuition and guess and check to come up with solutions. Okay, so now I have a family of functions that satisfies my differential equation. I've kind of, if I pick any function from this family, I've satisfied my first constraint here, that x prime has to be -2x. But I now need to consider the second constraint as well, that x of 0 has to be 100. And actually, nicely enough, uh, this is a pretty easy constraint to satisfy, not nearly as hard as the first one. On 100, on one hand, we're requiring that x of 0 equals 100. On the other hand, just from our model, x of 0 must be a times e to the 0, or just a. Well, hey, that tells me what I have to choose a to be. I have to choose of this family of functions, this infinitely many functions, a e to the -2t, parameterized by this a that can be any real number. I need to pick exactly the function that corresponds with a equals 100. So what's my solution to the initial value problem as a whole? 100 e to the -2t. So that's my solution to the initial value problem. This is my solution to the differential equation. And then my initial condition, this x of 0, gives me the value of that parameter that tells me what member of that family of functions I want to choose as my model. Something to note is that any any kind of coupled differential equation of this form, we call an initial value problem. So even if this was like x of 5 equals 100 or something, I'd still call it an initial value problem. So anytime that all of my information given is at the same time or the same independent variable input, then I call them initial conditions. So it's not so much the 0 here that makes an initial value problem, it's the structure, the nature of this problem. Any questions so far? Okay, so I think I'm going to cover things a little bit out of order here. And the reason is that I want to make sure we get through separable equations because I think that'll be more helpful for understanding the first order linear. And then we'll get as far as we can in direction fields. So because I have the first order linear supplement posted already, we're going to come back to direction fields. And maybe I will give just a little bit of insight here. Our solutions are functions, and a particular solution to an initial value problem is a function. So solutions to differential equations are families of functions, but solutions to initial value problems, or a solution to an initial value problem, is a specific function. maybe I should say the solution to an initial value problem is a specific function, just to be very clear what I'm trying to say there. Now, a function, a given function, y equals x squared or y equals e to the x, a specific function, can be kind of represented in three ways. It can be written algebraically. It could be described graphically, or it could be described numerically in the form of a table. Direction fields their goal, at least for first order equations, is to essentially directly generate a graphical representation of the solution for an initial value problem. There are numerical methods, like for instance, Euler's method, whose goal is to directly generate a tabular representation of the function to pick specific inputs and then estimate the outputs of the solution function for each of those inputs. And most of what we're concerned with in differential equations is coming up with algebraic solutions. Of course, if I have an algebraic solution, it's as at least with technology these days, it's pretty trivial for me to get a graphical or a tabular solution if I have the algebraic solution. It's quite difficult to go the other way. So if I can get the algebraic solution, I'm probably going to prefer that. And that's where most of our effort is going to be directed. And then we'll come back and discuss direction fields because it has a lot of tie-in with the geometry of how differential equations work, and possibly even a little bit on Euler's method, although I think that we'll probably leave that out. I really like differential equations, so I like teaching the course, and I usually put a little bit too much, admittedly, into Calc 2. But this isn't, most places do cover a bit of DiffEq and Calc 2, and I think what I typically end up covering is pretty close to about what like University of Pittsburgh covers in their Calc 2. So I've tried to model this off of theirs, but every once in a while I get a little carried away and want to cover something else just because I like the subject. Okay, so let's move on and talk about separable equations. And we're going to look at a motivating application, motion of a falling body. The book that I choose to use for DiffEq, the Nagel book, the author's last name is Nagel. One of the things I like about it is, most folks, at least at CCAC, are taking differential equations with the goal of going into something applied, like engineering or physics, something like that, maybe chemistry. So I like Nagel that at the beginning of each new chapter, when he's introducing some new, trick or technique to solve differential equations, he starts it with a motivating example, a motivating application. So that's one of the things I really like about that book, and I'm trying to do that here. So what's a motivating application for a separable equation? We could look at the motion of a falling body, and we could model the speed, v of t, this way. We could model it as dv dt equals g minus k over mv squared. Now, if we had no air resistance, dv dt, or the acceleration, would just look like gravity. Acceleration equals g. But if we ask what are the forces on the body as it's falling, well, there's the force of gravity, and there's the whole discussion about whether gravity should be considered a force, but we'll call it a force. The force of gravity is kind of pulling down at with the force mg. But then we have air resistance that's kind of pushing up, that's pushing in the opposite direction. So we'll give that the negative sign. And that air resistance, sometimes we can model it as just linear in terms of speed. Walter Lewin, the physics professor, actually has a really nice demonstration of this with dropping little like ball bearings through, like honey or through water or different substances. And sometimes the model seems like something closer to v to the first power would be a better model, and sometimes v to the second power seems like it would be a better model. So if you want more information on that from the physics side, that's, I think, a good lecture. But we'll choose to model it as v squared, proportional to v squared, the square of the velocity. So as you're falling down, gravity wants to keep making you fall faster, but the faster you fall, disproportionately, the air resistance pushes up on you, and we're gonna get to a terminal velocity, right? To where the influence of gravity pulling down is exactly equal to the influence of the air resistance kind of pushing back up. Okay, so, kind of interesting to think about what would it look like if this was v to the first power, but here we have v to the second power. Well, I noticed that I have dv dt equals function of v. If I thought of this dv dt as literally a division, some stuff with v divided by some stuff with t, and I wanted to solve for v in terms of t, I probably would do something like multiply both sides by dt and divide both sides by this stuff that only has v in it. That would let me get all of the v's on one side and all of the t's on the other side, and that seems like a pretty good first step to trying to solve this equation for v. So we're being very hand wavy here. And as I say here, wait, can we really do this? We'll look at some details in a minute here. But we can separate variables this way, or at least as a heuristic. And now it seems like, well, what should we do if we have differentials by themselves? They really make a lot more sense under integral signs. Can I integrate both sides? The right-hand side is simply t plus c, where c is some arbitrary constant. The left-hand side, if you want some practice with integration techniques, this is a good practice problem to do. You can either use partial fractions, or you can also use hyperbolic trig functions. Either one will work here. So if you want to, get fancy, you can do a hyperbolic trig substitution. Otherwise, you can do it a little more straightforwardly with partial fractions. But this ends up, the left side equals all of this stuff. And it's a bit of an algebra exercise. You put these together and you solve for v, and this is what you get. It's not the prettiest solution, right? I mean, it's got all of these exponentials and stuff in them. But if we set v of 0 equals v naught, things simplify a little bit. We see what a has to be. And if we set v of 0 equal to 0, so initial velocity is 0, we actually end up with v of t is just a constant times the hyperbolic tangent of some stuff. Right. So notice that the mass of the object does influence how it falls when we have the presence of air resistance, or in particular when the mass of the object is maybe relatively low, m is in the denominator here. When the mass of the object is relatively small, kind of relative to the other forces at play, this term is non-negligible. If the mass is very heavy, if we're dropping a bowling ball from a tower or something, the air resistance is going to matter too much, and it's not going to really matter how much that bowling ball weighs if it's about the same shape. But if we're dropping a beach ball versus a bowling ball and they're the same shape, this air resistance is going to have a lot to say about, say, when each of them hits the ground. Okay, but so the big thing here is we had this kind of trick where we separate the variables. That's why we call these separable equations. We can, if we do this little, kind of sketchy trick with the derivative, we can get, for equations like this, all of our dependent variable stuff on one side and all of our independent variable stuff on the other side, and then integrate. Okay, so if we have dy dx equals f of xy, where f of xy equals, say, g of x times p of y, then the differential equation is separable. If we have first derivative equals something that is the product of some stuff with the independent variable times some stuff with the dependent variable, then what we do is we separate variables this way. Dy over p of y equals g of x dx. We can integrate both sides. And then we have some, say, big H of y equals big G of x plus c. And that gives us, at the very least, an implicit solution to our differential equation. Okay, let's look at this example. Let me actually bump this to the next line because it is looking a little bit hard to see there. Can never seem to zoom in like reasonably on this program. I start to zoom in and it doesn't do anything, and then it like all of a sudden zooms way in. There we go. Okay, so let's look at this example. Dy dx equals e to the x over y squared. Again, let's do our kind of sketchy, kind of hand wavy y squared dy. We multiply both sides by y squared equals e to the x dx. Again, why can we do this? Well, we're going to see in a little bit here that we can legitimately do this. We're going to put both of these under an integral sign because that's where these kind of differential things make the most sense. Now, be careful here. On the left, our variable of integration is y, but on the right, it's x. So we need to keep that in mind. We're not integrating on the left side something like y squared dx. We're integrating y squared dy. So this is 1/3 y cubed. And on the right, we're integrating e to the x dx. That's e to the x. And don't forget our arbitrary constant c. Or I have that, say, y equals the cube root of 3 e to the x. And here I'll just say plus d. Well, d is 3c, but c is just an arbitrary constant. So 3 times some arbitrary constant is just some other arbitrary constant. Since writing 3c is just kind of annoying, I'll just write d. And that's the solution to this differential equation. This is not a solution that I think anybody would guess, right? This is a strange enough function on the right-hand side, or strange enough relation, that nobody's going to guess that this was the solution. But we now have at least one algorithmic method for coming up with solutions like this. We don't have to just rely on intuition and our knowledge of how derivatives work. We can solve problems like this. Now, it should be said that not every differential equation is separable, right? Not every differential equation, of course, is going to have a right-hand side that factors nicely into stuff with x times stuff with y. So that's why we need other methods like, say, first-order linear. If I look at this example, I have dy by dx equals 3x squared plus 4x plus 2 over 2 times y minus 1. This looks like a pretty terrible problem to try to solve. But actually, if I realize that it's separable, it's really not that difficult at all. This is 2y minus 2. 2y integrates, throw integrals on here. 2y integrates to y squared minus 2y. I don't need parentheses around there. I don't know why I put those around there. And on the right side, 3x squared, this integrates to x cubed 4x integrates to 2x squared, and plus 2x plus arbitrary constant c. Well, here I have an implicit solution. No big deal. We could leave it this way. If we really wanted to, really drive this home, we could, I guess, use the quadratic formula on y and come up with some kind of, something plus or minus the square root of a bunch of stuff. Um, but I think in this case, it's just much nicer to leave it as an implicit solution. This family of functions parameterized by c satisfies that differential equation, but we also have an initial value here, y of 0 equals -1. I might be a little confused here because y of 0 equals -1, what does that mean in this context? I don't have a y of x, nice explicit function. Well, really what this means is that when x equals 0, y equals -1. So I just, everywhere I see an x, I put in 0, and then everywhere I see a y, I put in -1. And that's 0 plus 0 plus 0 plus c, where I get 1 plus 2 equals c, c equals 3. So what's my solution to the full initial value problem satisfying both the differential equation and the constraint? What's my single member of this family of functions that also goes through 0, -1? It's 2x, and what did c end up being? 3 plus 3. That is my full solution to the initial value problem using my family of functions that solves the differential equation along with my initial condition to figure out what specific member of that family we're interested in. Any questions so far? Okay, let's look at another one here. So here we have a function x of t that we're looking for. Dx dt equals 2tx over 1 plus x. I'll try to make my t's and pluses not look the same. And here I might at first glance think, oh, is this really separable? But I actually do see that 2t on the top is basically like 2t times x over 1 plus x. So even though initially this looks pretty jumbled up, really it works out just fine algebraically. Or I have 1 plus x over x dx equals 2t dt. Now, as a side note, this constant 2, if you brought the 2 over to the left side and put a 2x on the bottom, that doesn't break anything. It's, you're going to get slightly different intermediate steps, but the end solution is going to be the same. Your solution might, look a little bit different for a little while, but we get the same function in the end. And then we want to integrate these. So integral 1 plus x over x is really just integral 1 over x, or log absolute x, plus integral of 1 plus x equals, I'll put my constant on the right. Integral of 2t is t squared plus c. Note that I only need one constant overall. If I had like a plus d over here, I just subtract d off both sides, and then c minus d is just the difference of two arbitrary constants, just another arbitrary constant. So I don't need bunches of arbitrary constants floating around. I just wrap all of that into this, this parameter c. This solves the differential equation. Again, it's an implicit solution. And then I can say when t equals 0, x should be 1. That is 0. So I see that c equals 1, and I have log absolute x plus x equals t squared plus 1 as the solution to the entire initial value problem. Any questions so far? Here's a short little argument why we can multiply by dx. Let's go through this really carefully. If I have dy dx equals g of x times p of y, let's let h of y be 1 over p of y. And we see that really, we see that h of y times y prime equals g. And we can integrate both of these sides. And note here that we are integrating both sides with respect to x. So if I have two functions that are equal, then their antiderivatives are going to be equal. Well, at least up to a constant, right? But on the left side here, I can just use the substitution rule. Here I have a y prime of x dx and a y of x inside of the function h. Well, that's just the same thing as integral of h of y dy. That's just basically a change of variables. And integral g of x dx doesn't, oh, I don't know why this by chain rule / substitution rule, but I put it as a fraction. So this is true by combination of the chain rule / substitution rule, whatever way you want to think about it, where basically dy equals y prime of x dx. So, I mean, strictly speaking, did I actually write that anywhere? I think I tried to be careful not to actually write that. But like strictly speaking, is it correct to say y squared dy equals e to the x dx? No, that's not really right. It's kind of only correct to say under the integral sign, I suppose. So, we're cheating a little bit, but we're not cheating that bad, right? We're eventually getting to a point where we're integrating everything and then moving on from there, and that is fully justified. Okay. Looks like we're not going to quite hit direction fields today, so maybe we'll leave that till next time. And I think we have a makeup day coming up pretty soon here, so I might adjust the schedule just a tad. But looking at our last example here, dA dt equals lambda a. So here a is our dependent variable, t our independent variable. And I can, divide both sides by a. And then multiply both sides by dt. And then integrate those. On the left side, I have, I guess it's log absolute a. Let's just call it log a. And on the right side, I have lambda t plus c. Well, this means that a has to be e to the power lambda t plus c. So that's my solution, a of t, to the differential equation. What should c be? What's a of 0? Let's just look at time 0. Well, that is e to the power. Well, that's 0 lambda plus c. That's just e to the c. E to the c is really just what a is at time 0. Let's call this a naught. Let's just, decide to call e to the c to give it a different name, a naught. So I have that a of t is, well, e to the lambda t plus c is just e to the c times e to the lambda t. That's just a naught, e to the lambda t. this model comes up all over the place. If lambda is negative, we have exponential decay, we might be looking at, say, radioactive decay, where A naught would represent an initial amount of radioactive material, and lambda would correspond to how quickly it decays, something like related to its half-life, something like that. If we were looking at population growth, maybe lambda is positive, where we have an exponential growth, and A naught would be the initial population, the initial amount of people or amounts of bacteria or whatever it is we're looking at that's growing, or initial amount of money, right? We might have money that is growing under compound interest. So A naught is just kind of the initial amount of whatever it is that we're measuring here. A of t is the amount over across time t, and this lambda is a parameter. If lambda is bigger than 0, it's the exponential growth rate, or if lambda is less than 0, exponential decay rate. Okay, and then in the supplemental material, we'll do a direct, well, it's already posted. There's a direct application of radiocarbon dating, and we see this same model. And here we're given a specific value of lambda. And then there's also just an interesting little application down here talking about using conservation of energy to solve a differential equation. So kind of an interesting little side note. I'm trying to throw in some different stuff from physics and course material that you might have seen before, or even that you might be able to use in a physics course. At some point I realized that like the key to solving like half of all physics problems, it seems like, is applying conservation of energy. Like if you just apply conservation of energy, really complicated problems just end up being so much simpler. So it's almost like a life hack for physics. Conservation of energy essentially always applies. And if you just apply it in a problem, a lot of times you can use that and leverage that to make things so much simpler. Okay, so we didn't get to direction fields today. So we will touch on that next time. We'll probably do direction fields and then start second order differential equations, then probably wrap up second order equations the next time, or maybe I'll push that to a supplement. All right, any questions on anything from today? Let me stop the recording.